Torque vectoring is an advanced vehicle technology that actively distributes torque between individual wheels to improve stability, traction, and cornering performance. Unlike traditional systems that send equal torque to both the wheels on an axle, torque vectoring intelligently shifts power to the wheel that needs it most, helping the car rotate better, reduce understeer, and stay stable even at high speeds or sharp turns. Let's look at the first image. Here you can see how torque vectoring helps during cornering. When the car is turning in, the system sends more torque to the outer wheel. This creates a helpful yaw moment that improves cornering performance and makes the car turn more naturally. When accelerating out of a bend, torque shift again reduces to reduce understeer. So instead of the car pushing wide, it follows the driver's intended path. So the key idea is that independent wheel torque control gives the vehicle sharper handling and much more stability while cornering. This is an image of yaw moment generation. A car rotates along its vertical axis, which is known as yaw. By applying unequal torque to the left and right wheels, the system creates a desired yaw movement. For example, if a car needs to turn left, the controller can send more torque to the right wheels. See less in the image. This pushes the car to turn into the turn and rotate it smoothly around this axis. Electric vehicles can do this even better because each motor can instantly change torque within milliseconds. So torque vectoring basically works as an active rotational control system for the full car. This is an image where you can see the torque vectoring corrects understeer. The image shows how torque vectoring helps when there is understeer or the loss of traction. Here each wheel receives a different torque value. This sequence is 125 and the budget is just 43, and it's completely depending on the grip levels. By sending more torque to the wheels with better traction, the system keeps the vehicle stable and prevents sliding. This also accounts for load transfer. In straight line driving, the load is evenly distributed, but during cornering, more load shifts to the outer wheels. Torque vectoring uses this information to actively redistribute power, giving the car maximum grip and much more confidence while cornering. This is a generic diagram of how torque vectoring works. It starts with sensor, wheel speed, yaw rate, steering angle, and many more. Then we sensor feed in data to the vehicle state estimator, which calculates slip, ERR, the vehicle's actual versus expected behavior. The information then goes to the torque vector controller, which decides how much torque each wheel should receive. Finally, the command goes to all the four wheels independently. This is a form of complete closed loop control system. Now let's look at history of torque vectoring. It all started with just open differential, which allowed wheels to rotate at different speeds but had no control. Then we got limited slip differentials, which improved traction but still couldn't actively control. And the original torque vectoring concept using electronics started in the 2000s, where active torque vectoring with smart ECUs distributing torque side to side. Then from the 2020s, the EV torque vectoring started, where each wheel has its own motor offering instant and independent torque, which is the ultimate form. These are some of the iconic cars that introduced major torque vectoring milestones, from the Honda Prelude to modern EVs like the Rivian and Audi e-tron-s. So overall, torque vectoring is a key technology that enhances vehicle stability, safety, traction, and performance, especially in modern electric vehicles, where precise and instant torque control is possible.
Let's check out some control mechanisms for torque vectoring. The most simplest one is gain schedule PID control. So what we do in this is that for various steering angles and vehicle velocities, we find the optimal PID constants, which we can provide to this equation, which generates the required yaw moment to be given to the vehicle. Based on the optimal PID values, we generate a cubic interpolation of these points and then correspondingly map to any vehicle speed and steering angle input we receive. Now, this method is reactive to the yaw rate error and does not anticipate the future states. It is cheap, lightweight, and fast to implement, but limited. Now, fuzzy logic based controllers are better at handling non-linearities compared to PID. It uses a rule-based system instead of mathematical model. As you can see, membership models are made to model the amount of truth. Now let's see our your rate error is zero point 0.5, negative zero point 0.5. So basically, it can fall in one of these five classes. It, as you can see here, it falls 25% in negatively small and 75% in negatively large. So correspondingly, we have these rules. Now, negatively low corresponds to increasing the corrective torque highly. So basically, we go here and we consider 75% of this curve, and since ns corresponds to is, we consider 25% of this curve. So what is typically done is that we take this newfound area and then find its centroid to give our required corrective wheel torque. Now there is no guarantee that this solution is mathematically optimal, but it is a good way to model the nonlinearities. Another drawback is that as the number of inputs increases, the rule base may increase exponentially. MPC is a high accuracy model which also considers the future state, and thus it gives a very fast response. In this paper, it tries to minimize both the power consumption and also uh, provide maximum cornering stability. I- In the linear MPC model, we consider the power delivered to the motors, mechanical power delivered to the motors, which is torque into omega, and add this term in for convexity of the function. Now, the future next state is calculated by using this equation, which takes in the current state, the current torque input which is given to each wheel, and the steering angle. And based on it, it considers the vehicle model and generates the next state. It tries to minimize two loss functions, that is, this one to which ensures stability, and this one which ensures power, which ensures the energy efficiency. As you can see here, it looks into end states into the future. You can also see some weights here. So as you can see, W1 and W2 increase with delta, and W3 and W4 increase exponentially when delta is smaller. This is used to these weights are given to the yaw rate and the side slip angle tracking, and these weights are given to the speed tracking and energy efficiency. These weights become large when we are cornering or delta is larger, and these weights become larger when the car is traveling along a straight road and delta is smaller. We then use this cost function to finally determine the optimal state.
Coming to LQR, a linear quadratic regulator, this is one of the basic controllers which again uses the bicycle model as we have seen before, which is a linear state space. And the quadratic part comes with the cost function, which you can see here penalizes any errors in the side slip or yaw rate. The reference side slip is zero, which we don't want any side slip. And the reference yaw rate is calculated as we've seen before using the driver's steering input and the vehicle velocity. We also wish to penalize control effort or the yaw moment, which in this case is denoted by mz. And to minimize this cost function, we first form the Hamiltonian, which is a combination of the current cost and the future system, which is represented by these terms. And to solve this, we use the co-state equations. And on solving, we have to use the solution of the Riccati equation to get the final yaw moment equation, as we can see below. This expression is static, which is one of the biggest drawbacks of LQR in this case, where a static LQR means that we initially estimate the vehicle parameters, and once we form the final yaw moment expression, we don't update that at all. And throughout the lifetime of the vehicle, it uses the same equation. So we don't adapt to any changing conditions around us. Maybe the friction changes, the mass changes, motive inertia. We don't account for all those. So that's one of the drawbacks. And so to account for this, we have MRAC or Model Reference Adaptive Control, which as the name suggests is an adaptive controller, meaning it updates dynamically in real time. As we've discussed before, we do have vehicle speed and driver steering to generate the reference yaw rate, and this goes to a third order reference model. What's meant by this is that when a driver makes an action, like turning the steering wheel, we want the vehicle to react, but it can't react instantaneously. So in a reasonable amount of time, let's say 0.2 or zero point 0.3 seconds, we want the vehicle to reach that desired yaw rate. So to do so, we place two of the poles strategically to have a desired rise time, fall time, and overshoot. And the third pole is placed far to the left in the left half plane to make sure the system is stable. So these outputs, if we had used these outputs, it would have been a static system. So to make it dynamic or adaptive, we use these as inputs to our MIAC controller, which also checks the error in the actual yaw rate, side slip angle, and the outputs of the Aurora model to dynamically update using the Lyapunov updation rule to get the desired yaw moment. So this dynamically changes the gains, which we can see here is K and KZ, where X represents the state space variables, the yaw rate and the side slip angle, and Z is the integral of these errors. And the whole state space equation can be represented here. And so this goes to the torque allocator, which again can be a simple torque allocation, which I've seen before, or it could be something more complex, like optimizing something, like the energy or the power. And this then distributes four torques to the wheels. So moving on to reinforcement learning, which is one of the most complex controllers, and I've focused on the TD3 TTPG, or the twin delayed deep deterministic policy gradient, which is an improvement on the basic RL controller. So here we see the reward function has two parts. The first reward function focuses on rewarding safety, whereas the second part rewards energy use. So in the first part, we reward minimizing the error in the side slip and yaw rate. We also don't want the system performance to degrade. We don't want to exceed the system constraints, meaning how much the motor can actually handle. And the second part, we want to minimize the control effort, or so because it's a continuous time algorithm, we don't want a sudden increase in torque or a sudden increase in the current flow through the circuits. So we want to minimize the delta U, or the increase in torque, and we also want to minimize the power input to the motors to take these collective action. So here we see the active critic architecture, where the critic and actor are two different neural networks, where the critic network tries to predict Q, which is the combination of the current reward based on the action and the future rewards based on what state we are going to. And the actor network is the more important one, which actually produces the full torques which will be going to the wheels based on the current state. And so the state space isn't the basic 2 degree of freedom as we discussed before, but it has 8 degrees of freedom, all related to the yaw rate and error in yaw rate, the side slip and error in side slip, as well as the longitudinal velocity and error in longitudinal velocity. So what happens is that the improvement in this case is in three different parts. The first improvement, as we can see here, is that instead of having a single critic network, we have two target networks, and both of these keep updating. Based on whichever of these produces the smaller Q, that is passed to the actor network. And why do we do so? It's because overestimation of Q is one of the biggest flaws and biggest mistakes that can happen in this architecture. Additionally, we also intentionally add noise to these four actions so that in the initial stages we can explore more states, and also the model can't overfit because we're adding noise. And the third thing is that the actor network is not updated as often as the critic network. So the critic network is updated maybe every zero point 0.3 seconds, whereas the actor would be updated every second or so. This is so that the critic learns a more optimal policy, and the actor doesn't need to go to local minimas, or unoptimal policies need not be learned. Initially, we explore a lot of different states to build up experience replay memory, which could be around maybe a million different samples of current state, next state pairs. And we sample a mini batch of around 64 samples and constantly keep retraining data critic networks. And this is also, again, a dynamic system, but pretty computationally expensive. But this produces some of the best performance compared to other algorithms which we've seen before.
Picking up from the control theory, I'll now walk you through the simulation and validation phase of our project. Our goal here was to take those theoretical algorithms and prove their viability on a virtual vehicle. Specifically, we set out to validate three performance metrics: understeer mitigation, can the controller actively fix the vehicle's path; stability at the limit, does it hold up when the tires reach saturation; optimization, can we mathematically tune these controllers to be energy efficient. To test this, we moved beyond standard linear models. We implemented a non-linear 2 degree of freedom bicycle model using the magic formula. Unlike a linear model, which assumes infinite grip, our model captures saturation, the point where the tire loses grips. This allows us to realistically simulate skidding and loss of control, which is the only way to truly stress test a stability controller. We parameterized this model to match a Formula Student electric vehicle: 300 kilogram mass, high grip slicks, and low inertia. Crucially, we constrained the simulation with the physical limits of our powertrain, capping the yaw moment at 275 newton meter to ensure our results are achievable with real hardware. The control strategies implemented was a PD controller, an LQR as our optimal control benchmark, and a gain scheduled PID as our proposed robust solution. However, a controller is only as good as its tuning. To ensure a scientifically fair comparison, we avoided manual tuning. Instead, we used the differential evolution, a genetic algorithm, to numerically optimize the gains for all three controllers against the same objective function. minimizing tracking error while penalizing motor saturation. For the PID controller specifically, the optimizer generated these 3D control surfaces. This effectively creates a lookup table where the gains automatically drop at high speeds or high steering angles. This breathing behavior prevents the instability and noise amplification that usually plagues simple PID controllers at the limit. Moving to the results. At 15 meters per second, we can clearly see that both LQR and PID outperform the PD baseline, which suffers from phase lag and understeer. At this speed, the PD controller achieves the tightest tracking with RMSE of 0.177. At lower, safer speed of 10 meters per second, the PID demonstrates near perfect tracking with an RMSE of just 0.038. This confirms that within the linear region of the tires, the optimized PID offers exceptional precision. Finally, we ran a stress test, the accelerating slalom. We ramped the speed from 10 to 25 meters per second mid-maneuver. While the fixed gain PD controller degraded into understeer, the gain scheduled PID maintained accuracy throughout the entire acceleration phase. This validates that adapting gains in real time is necessary for dynamic racing scenarios. Looking inside the controller, you can see the proportional gain dynamically dropping during peak turns. This is the controller backing off to prevent motor saturation when the tires are already at their limit, ensuring stability without overheating the actuators. In conclusion, the PD controller serves as a simple baseline but lacks range. LQR offers the best smoothness and energy efficiency, while gain scheduled PID delivers the highest performance where tracking accuracy is paramount. Thank you.